Hello everyone. It's my pleasure today to host the MPI monthly seminar. And today I'll talk about some of my recent research at Princeton entitled Approximate Data Structure for Detecting Heavy Flows. So my research focused on network measurement on programmable switches. First of all, why we need network measurement? People often imagine the network just works. However, today's network is actually fragile and easily breaks down when lacking management. Managing today's network is very challenging for several reasons, including outages, attacks, and congestions. Network measurement can help operators cope with these challenges. First, by carefully managing the diverse applications running on the network and understand their performance bottleneck, we can better configure the network for each type of heterogeneous workload and provide better application performance for users. Second, network measurement can help network operators monitor cyber attacks and potentially respond faster. And last but not least, accurate measurement can help network operators do capacity planning and better prepare for future workload. However, network measurement is not easy. Existing methods such as SNMP and NetFlow are inadequate for several reasons. It's just like finding a needle in a haystack, there's never an easy way. Uncustomized network measurement like SNMP will only do bulk aggregation and does not provide any detail regarding every packet or every network flow. And meanwhile, NetFlow, which does sampling, gives us some detail for some traffic, but it does indiscriminate sampling and give us some random boring traffic rather than the interesting part. Let me give a quick example about why we need better measurement rather than this uncustomized measurement. I will take the example of microburst. What is microburst? In normal traffic rates, network traffic are much slower than line throughput. So the queue in the network switches are mostly empty and there's no buildup. However, occasionally there are a fast burst of traffic coming into network switches and cause some queuing. It will cause significant queue buildup in a really short time, and immediately the queue will be drained. If you look at any aggregated measurement, the average throughput or the average queue length or the average of anything will be normal. However, the customers will experience higher queuing delay and packet drops during this very short time period. Traditional measurement cannot really help us diagnose these problems. Today, we have the new opportunity to do measurement in data plane. Data plane means the lower level of fast forwarding plane of the programmable switches, and in comparison to the control planes, which are the higher level forwarding rule definitions in today's network equipment. The opportunity we have today is to see per packet metadata a very short time scale. The short time scale means for every packet, we can run some small algorithm to try to perform measurement, but based on this every single packet. And secondly, we can run flexible queries for different operators' need by programming on these programmable switches. And finally, we can take per packet action for these packets. So based on the measurement result, we can immediately adjust the behavior of our programmable switches. However, given this opportunity, we always also have some challenges coming with it. The challenges are mostly on programmable model, that we can only have a very restricted set of computation we can perform on these programmable switches. And secondly, we'll have a limited memory size and limited memory access on these programmable switches, which restricts the accuracy we can get for our measurements. These challenges are not just for our particular programmable switch hardware, but are more or less fundamental for any high throughput network or high throughput processing, because today's computational hardware cannot really catch up with the speed of the network, and network is getting faster and faster. We have to have novel ways to try to simplify our computing in order to do measurement. To deal with the limited memory, we need to do the right data reduction. We can't save the entire traffic, which has ON size, or the entire haystack in the very small programmable switch. This is essentially needle in the haystack problem. If we, traditionally what we do is sampling. We pick two random heights and say, this is what we need. However, we know the measurement answer we're interested in is only size, constant size. So if we can capture the right data or using the right data reduction, we can still get approximately the right answer saving the memory and still does not use so much memory we cannot afford. As an example, this is the flows coming in, this is the traffic coming in. We don't know which one is the needle, but once we saw it, we actually can save the answer inside our memory, which is very slow, and the traffic still goes through the switch. Today, we'll talk about two related network measurement projects, both run inside programmable switches. The first project tried to find heavy hitter on the link, or during a specific time duration, which flow send the most amount of traffic. Note that this is possible to use sampling to achieve a similar measurement on the link. However, our algorithm can provide somewhat a better accuracy given the same amount of memory. The second project is more interesting in that sense that we try to find the heavy flows in the queue or in the queuing buffer at any given time period. Previously, there's no work that allows us to gain the visibility to see which flows are in the queue. Occasionally, some flow will send a burst of traffic leading to the microburst we described earlier and cause a high delay or jitter. We'd like to understand which flow contribute to such buildup. However, if you look at the link level, there are only very short flows and does not contribute to the heavy hitter flow on the link. And that's why we need to find who's heavy in the queue. For now, I'd like to pause a moment and try to ask a few questions for everyone and try to see if anyone have questions to me. The high-level takeaway before we start is, first of all, we need compact data structure to meet data plane constraints. And the first project PRECISON was trying to do branch prediction or to use a simple way to recover, use a simple way to normally and recover the mistakes we made in data plane. And the second one, Project Snappy, will try to approximate measurement with resource accuracy trade-off. So right now, before we start, we should first have some question in mind. And my question for everyone will be, what will be needed when we run every algorithm in the data plane? Or what's the difference between, or what can we get out of it when we have better measurement technique to measure everything? And I will also welcome any question from me before we go ahead. Okay, I guess we should just move on for now. And so today's talk, this is outline of today's talk. I will first give an overview of what's in the PISA programmable switch. And then I will try to describe what's the first algorithm, PRECISON, which is trying to capture heavy flows on the link. And then I will describe the second algorithm, Snappy, which is trying to catch heavy flows in the queue or who's causing microbursts. And finally, I'll give a summary and hello? Am I disconnected? Let me see.
We hear you just fine on this end.
Okay. Let me move on. So then I will give a summary of today's work, or today's talk. So as a teaser, as you may already heard of, most researchers in the Network Programming Initiative will work on programmable switch modeling using the protocol-independent switch architecture, or PISA switches in short. This is a quick high-level overview of the PISA switch architecture, but maybe if anyone's interested, I will be happy to give more details. So basically what happens in the programmable switch in PISA architecture is when a packet comes in, it comes in as a byte stream. There's a parser that can parse the byte stream into some headers. Basically it says source IP is blah, 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 destination IP is blah, blah, blah. I'm using UDP protocol, for example. In my research, I usually don't touch this part, but just to let everyone know that parser is also programmable. Then the packet will traverse through the ingress pipeline that will try to look at some match action, perform some match action. Match will match on some of the packet fields, and the actions will be, for example, modify this packet, like for example, write the egress port to decide where to go, or modify some of the fields inside. So here we can do multiple stages of match action, and the matches are always on the fields, and action can action on this packet. So for example, we can also do some stateful actions on the packet to save something in the memory. So for example, here we can try to count how many packets go to each port by matching on the egress port and writing some value to say, okay, this port has one more packet. And at the end of, we can also modify something in packet. For example, the action could be to subtract the TTL value by 1. So here the value was 64, we change it to 63 and write it back to the packet itself. And now the packet we decided where to go, it will go through a switching crossbar, and the packet will go to one of the egress pipeline where it will experience some queuing before. So the packet is queued into the queue, and when the packet was departed from the dequeued from the queue, it will go through a similar egress pipeline. The pipeline will also at the egress pipeline, we can also see some metadata about what happened in the queuing. For example, the queue length, what time does it enter the queue and what time does it depart from the queue. Egress pipeline can perform similar thing on match action, save something in the memory, etc. Before the packet is departed into before the packet go out of the switch. At the departure part, the packet go back into a byte stream, and then it ends the lifetime. The byte stream can either go to the next hop, or we also have the opportunity to recirculate the packet and go through the entire pipeline again if we haven't finished the programmable processing of the packet. Here, I'd like to elaborate a little more on what's happening under the hood. So what happened inside each switch is, what happened in each stage is we have both pipeline memory or stateless memory and some register memory, which are stateful memory. The stateless memory part is when the packet comes in, the memory will carry alongside with the packet. Here, given the example that in the pipeline, packet number n just entered the stage. The packet will enter the entire match action unit, and then we'll have the opportunity to examine all the match rows against the packet. Some of the match rows may want to update some of the memory in that stage, and some of the match rows will update the packet itself. Say that the first row says something the memory should be updated. The update memory instruction will now change some value in the stateful memory, and then it will stay there, and the next packet comes in, you can see it. The other part about updating TTL will update the packet itself. So the new packet will have an updated TTL value going to the next stage and going to the next pipeline memory. Now the new packet will come in, and the new packet will go in, and on and on and on. For network measurement, we're mostly interested in updating the register memory part because the packet transformation is mostly for routing, etc. But we need a memory result somewhere. We save the measurement result inside the register memory, inside the switches. The pipeline processing gives us some programming constraints. So for example, each stage only performs a simple action. It's necessary to cope with 100 Gbps or more line rate and processing every packet a few nanoseconds. And also memory are partitioned across stages. Basically, the memory you save in one stage is not visible from other stages. So for example, when the packet comes in, you could read from value from memory A, and the value comes in, you can read some value from memory B, and then when the packet comes to the end, you can read some value from memory C, but at this point, it's too late to update anything in memory from array A. This is necessary constraint for pipeline processing because if you want to access across pipeline, we'll get some issue like concurrent access, hazards, etc. Again, these constraints are more or less fundamental for high throughput packet processing and not unique for our own hardware. So as an algorithm designer, we should be aware that when we design algorithm, we can take this constraint in mind and design better algorithm that's easily adapted to this hardware. So in summary, the challenges to run any algorithm on PISA architecture are, first, the memory are partitioned. Second, each stage can only perform simple arithmetic. Third is we have limited memory size and we have limited number of stages on hardware. The first two are more fundamental, and the third and fourth will turn out to be just a nominal one, as we will see soon. Our solution is to do approximate measurement everywhere. Since precise measurement is infeasible in hardware, we can use approximation. And approximation is not sampling. Precise measurement requires more memory and require complex processing, and it's very hard to run at line rate processing every single packet. In the meantime, approximate measurement can save memory by using data structures such as sketches. And it only use simple logic and become hardware friendly. We can perform other arithmetic on the hardware. And finally, people may have concern that approximate measurement is less accurate, but it's not the case. We can show that we could get variable accuracy memory trade-off and provide more and more resource to get better and better accuracy, up to the point that being required by the application. This is my personal research interest that approximation is okay for a lot of applications I can think of. I'd like to ask audience that which application can use approximation, which application cannot use approximation. Anyone have any idea now? We can have a short discussion, or we can also postpone this to later in the talk. Oh, by the way, if anyone wants to share some thought with me, please unmute yourself so I can hear you. Okay, so I guess I can move on. And the question here will always be bugging me every day that what can be approximated and what should not be approximated. So now let's move on to the first algorithm called PRECISON, which is called catching heavy hitter flows on the link. First of all, what is heavy flows or heavy hitter flows? So in traditionally in network traffic, there are always some flows that are very heavy that occupies most of the traffic, and most of the flows are just very, very small. And conventionally, we call them elephant flows and mice flows. Elephant flow are those who consume most of the traffic on the line, and mice flows are those who are just sending a few bytes. This phenomenon is not just observing; it's observing every network. So in our daily life, for example, like T-Mobile says only 1% of their users use more than 50 gigabytes of traffic every month, and most of their users only use like a few hundred megabytes, for example. So we want to, in measurement, we want to catch these elephant flows, and there are two ways to report these elephant flows. The first way is to say, can you report the top K flows in the network? And second is, can we estimate the flow size of each flow in the network? So for the first case is at the end of the day, please give me all the flows you believe is top K flow. And the second was, for every packet coming in, please report a flow size and tell me whether this is elephant flow or not. A very traditional solution, traditional algorithm for finding heavy hitter is the space-saving algorithm. Let me give a quick introduction about what's the space-saving algorithm. So say that when a packet comes in and have this flow ID, we'll try to put this flow inside a counter. And here we have two counters, up and bottom, and we first put this flow into the top counter. When the second flows come in, we'll put it in the bottom counter because we have empty counters. Now, say that we have a third flow come in. There's no empty counter, so we try to find an empty counter for him and put it in. And if the flow come in, we already have an existing counter, we'll try to reuse the counter, just increment the count to 2 here. So now this flow will come in and try to increment his own counter. And this flow comes in again and increment his own counter. So both of them have count 3 now. And one more comes in. Right now, there's another flow comes in and says, I want to be counted. We'll try to find the minimum counter for him. So now this is the minimum counter. We find it. We replace the new flows into it, and then increment the count as well. So now say that we keep having new flows coming in, and then we should always find the minimum counter to replace it whenever we have a new flow coming in. As we can see, space-saving algorithm doesn't work quite well at the end of the day because 2 random new small flows just get counted, and we thought they are all the heavy flow we have. Some people may have a question that why don't you just erase the counts when the new flow come in, you never see it. The reason is because the smallest counter is too small and the other counter is so large that if every time you come in, you erase the smallest counter, you will never have a large counter in your system. So we still need to keep the largest count. Space-saving algorithm is widely used in real-world applications, in a lot of database systems especially. However, the performance of space-saving algorithm will suffer when there are too many small flows, which is exactly the case in networks. In database communities, they have a few large flows and few small flows, or I shouldn't call it flows. But in network, we have a lot of those mice flows that will just come in and stress the system, and we can never maintain a good list of large flows. And this is why me and my collaborators propose a random emission policy, that we don't always evict the small flows when we run out of memory. So when minimum counter is seen in, we'll try to evict the smallest flow with a probability of P. And if we want to say we increment 1 by expectation for a new flow, we want to try to write a probability as P equals 1 over CMIN plus 1. So at a high level, the idea was if I see one new packet from a new flow and I don't have enough memory, in expectation, I will give you a count 1. So in using probability, we can gain accuracy, but we do lose some probable bounds from the original algorithm. However, we can use experiment to show that this approach is still pretty accurate. Let me give a quick illustration about how random emission policy will work. The RP algorithm works similarly at the beginning when you have enough memory. However, when there's a new flow come in and you don't have enough memory, we try to count this flow nevertheless and try to flip a coin for this flow. So recall that now, right, the smallest count is 1, so probability is a half. So we try to flip a coin. And maybe the coin flip will land as a tail. So we decided maybe we shouldn't let this flow come in. Now packages keep coming, and it turns out this is a heavy flow. So it will come again. When we come again, we'll try to compute the probability again, and we'll flip a coin again, and maybe it goes in. So later on, flow just keep coming. And when a small flow comes in, it will just get another coin flip. Maybe you'll get denied. And because the counters are growing larger and larger, if the flow was not really large, but just a randomized flow, it will just come occasionally once or twice. It will not win a coin flip. So it will never go into the system. So the counters will accurately maintain the largest flows. In reality, we'll have much more than 2 counters. And so we always get a case to get the top K counters right, or the top K flows right. However, the RIP algorithm was not directly applicable to be run on programmable switches because they're designed for general purpose CPUs. We have a lot of constraints in the programmable switch. For example, the partition memory does not allow us to know the global minimum counter. And it's too late to update the memory once we know which one we want to update. Also, we cannot precisely sample probability, and recirculation hurts throughput. Now I will try to explain in detail how we adapt these algorithms to run on our PISA programmable switches. So for the first constraint, we cannot really find the minimum in the array. So say that, what if you can only read and write 4 memory slots per packet? So now there's no way we could find the minimum global value, Cmin. We want to try to find an approximate minimum C prime min by randomly querying 4 address based on the flow ID. So say that we hash the flow ID, use a hash function to randomly find 4 slots across 4 stages. And now based on the hash value, we know that we want to look at these 4 entries. So after the 4 entry, we just find the smallest out of these 4 rather than the global minimum. And maybe another flow will come and we'll look at some different entries. Maybe some of them will overlap. And we'll try to find the minimum of these 4 entries and tell them this is the minimum you get. This idea was adapted from the famous counting sketch and also the idea about hash pipe. So this is not a trick I invented, but it's very useful. The second issue is we know the approximate minimum too late at the end of the pipeline. And by that time, we know that the number 3 was the minimum, but it's too late to increment it to 4. So we know that this is the thing we want to update, but we cannot really update it now. The solution is to use a little bit of packet recirculation. We can recirculate the packet from the end of the pipeline to the beginning again, only if the coin flip succeeded. Previously, algorithm hashpipe choose to never recirculate, and then they also consider recirculation, but say it will hurt throughput too much. But however, this actually hurts accuracy too much if they choose not to recirculate. Our solution is you do it only a little bit, so you will not hurt throughput, and they also boost performance a lot, boost accuracy a lot. So once you recirculate, and then you update. Thirdly, there's another constraint that we cannot precisely sample probability. We need to flip a coin with probability 1 over seeming plus 1. So for example, 1 over 100, 1%. However, arbitrary coin flip or arbitrary probability require division and random sampling. But we only have these random bits in the data plane. We cannot really do random sampling. So what we do is we use a naive solution to try to sample probability based on up to the nearest power of 2. So for example, if you want probability 1/3, I will approximate using 1/4, so essentially flipping 2 random coins. And if you want a probability of 1/5, we'll approximate that to 1/8, so flipping 3 random coins. This is essentially a 2 approximation of the probability P that's a slightly under approximated. There's also a better solution to use match action table in the switches to achieve an even better approximation. However, due to time limit, I will omit this detail, so we can refer to the paper for this. And finally, the concern here is the data plane, the recirculation in the data plane will hurt throughput. So we should, for example, if you recirculate a packet before sending that out, we'll have a packet reordering issue. The solution is to always send the original packet and recirculate a copy of that packet. So we does not cause reordering for TCP flows. It will not cause throughput degradation. And finally, we may worry that there are too many recirculations. So for example, we can have recirculation every single packet. At the beginning, everything's 0. The solution is to initiate all the counter to 100. So in this case, like if the flow has smaller than 100 packets, it will not ever be counted. And if it's more than 100 packets, maybe it will come in and have a count of 101, 103, etc. Because initial value is always more than 100, the recirculation probability will be smaller than 1%, which is acceptable for most applications. So given all these constraints, now we can present what's our algorithm. The precision algorithm is as follows. We'll visit three randoms. This is, say, D equals to 3 random entries, 1 per stage, across 3 different stages of the pipeline. If the flow ID matched, we'll increment it by 1. So for example, if this packet comes in, otherwise we'll flip a coin. For example, if this packet comes in with flow ID Z, first, based on the hash value of the flow ID Z, we'll hash it to 3 different entries, like these 3. The packet will go through the pipeline, and then at the end of the pipeline, it realized it will never belong to anyone. It didn't increment to anyone. So now we look at this entry, which has 102, the smallest across the entire system. Across the 3. Not entirely smallest, but quite small. And now we'll flip a coin, and the coin flip probability is very small, 1 over 103. If it's very lucky and the coin flip succeeded, we'll just go the packet recirculate, and the original packet will go out, and the clone will circulate. And we'll try to find the corresponding stage and update the minimum counter here. So now the counter will go up, and we also rewrite the flow ID. So now flow Z will have its own counter. So at the end, if you want to query, we just look at this memory and look at which flow ID have a counter, which means it's potentially a heavy hitter. If you want to know the top K values, we compare all these counters and find the largest K counts to get a top K flows. Due to time constraint, I will not present the entire evaluation of the algorithm. However, I would like to give some highlights. By adapting to data plane, we introduce some issue. For example, when we recirculate, we will impact throughput. So the answer is if we bound probability to 1%, we actually can successfully get less than 1% packet recirculated. And we didn't see any accuracy loss here. So if we bound the probability to 1%, people may imagine you don't have enough chance to update your entries and the count you maintain was not correct. Well, the result is most of the time your answer is off by less than 100. And the second issue is when we recirculate the packet, the update gets delayed in some way because the recirculated packet needs to go to the queue again, come back again, and update the memory. We also see that there's no accuracy loss here. Probably the reason is it's already a random event. If you delay a random event, no one will actually know that it's delayed. There are other potential problems. For example, we're approximating the coin flip to using only random bits. The result is 2 approximation is good enough, and if you use a better approximation described in the paper, we actually see negligible difference in accuracy. And finally, people may be concerned that I don't have enough stages in programmable switches, so we don't have the chance to actually run the algorithm using many stages. And the result we see is actually quite amazing. 2 stages are already very good, and if you have 4 stages, you can't really distinguish that from infinite number of stages. The intuition behind this is you have a power of 2 choices, that if you only have 2 slots to update, you can choose from one of them. It already gives you very powerful. So if say that you have a hash table, but you're not allowed to have collisions, then you get very bad performance. But if you use Kuka hashing, which allows you to use 2 entries rather than 1, you get very, very good performance. I will skip the details in the evaluation and go to the summary here. So the precision algorithm is trying to catch heavy flow on the link. It's an accurate and hardware-friendly algorithm to detect heavy hitter flows. The takeaway here is we're using approximate probabilistic recirculation. It's very hardware-friendly because normally we don't do recirculation, but only do that for a rare case. And for a normal case, the packet simply goes through the entire pipeline. They have little impact on throughput and have better accuracy than most existing algorithms doing heavy hitter detection. Now we can have another question that we can think about and discuss offline. That is, what other optimization can we achieve using this probabilistic approach? So normally, when people design algorithms or people write programs for programmable switches, it's actually quite deterministic. Like packet come in, if else, if this go that, else go that. It's all deterministic. However, when we do measurement, we can free ourselves from this paradigm and think about, can we do something probabilistic? Because when we do probabilistic, the program becomes simpler, and maybe we can recover from a rare case that's more challenging. In the normal case, it's very easy to fit in programmable hardware. Okay, now let's move on to the next section of the talk, which is the algorithm Snappy, catching heavy flows in the queue. So again, let's revise what's a microburst. In normal case, the packet comes into the switch very slowly, and then there's usually no queue buildup. So the queue here is essentially, some people call it buffer. It's the same thing. The packet will wait in the switch before sending out to your port because of contention. Queue buildup is usually minimal in regular switches. However, if there's a burst come in, there's a traffic backlog, and then people have higher queuing delays. And usually this will just go away quickly. Microburst really exists. It exists in both carrier and data center. And the microburst also cause a lot of problems. As a network administrator, we may have some conflicting goals. We want to avoid packet loss, use cheaper switches, achieve higher link utilization, but still want to support bursty workload. This looks like a mission impossible, because once there's bursty workload and the link is already highly utilized, the burst will cause queue to grow up. Cheap switches will have shallow buffer, and then it will run out of the queue. Sorry, it will run out of the buffer space, so new packet cannot come into the switch, and we'll have some packet loss eventually. We try to make it possible to support both of these goals, but primarily by trying to find out which workload is bursty. So we try to penalize only the bursty flows while still support other flow to go smoothly through the switch. So now our goal was to find out who caused the microburst. Let me try to give a clear definition about what's the flow who caused microburst. There's a general queuing occupancy problem here that we want to solve, which is what's the size of each flow in the queue. Given at any given time, there are some packets in the queue. We try to know that which flow contributes to the entire queuing buffer. For example, in this case, the green flow contributed 5 packets, while the blue flow contributed 1 packet, and the orange flow contributed 2 packets. Snappy tried to only solve this subset of this general queuing occupancy problem because it's too hard to solve the general version. We try to identify which flow belongs to a heavy flow in the queue. So here we'll say only the maybe orange and the green flow are heavy. Other flow are just only have 1 or 2 packets, they're small. And secondly, we only care if the queue is very long, because when the queue is very short, there's no delay, no problem, but only when the queue is long, we say there's a high delay. We try to see which flow are heavy. Even if the queue occupancy problem is very hard to solve, let me try to show why. So when packet comes in, we can maintain a counter to say these packets have size 1. However, this part is not challenging. However, the challenge comes when we packet depart the queue. When this packet comes out, the packet will go. We want to decrease the count in some way. While new packets come in, we also want to increase the count. Now we realize that we need to update the memory from both ends of the queue. When packet enter, we update something. When packet leave, we still update something. And update on both ends is very hard because memory is partitioned in our system. We cannot really access the same memory when packets are coming in and going out. Again, this is not just true for programmable switches, but true for any system, because both streams are coming really, really fast. And if you use both of them to update the memory, you are definitely getting some memory contention or hazard, etc. Snappy tried to solve this problem and fit this measurements text into the programmable switch. We solved the first problem of cannot add and delete simultaneously by using snapshots. I will introduce what's a snapshot later. And second is we have a restricted computation model in data plan that does not allow us to do random arbitrary counting. The solution is to use sketch or approximated data structures. And finally, the problem is microburst is transient. So even if the measurement is available 1 millisecond later, it's useless because microburst should be already gone by then. The solution is we should use immediate action in data plan. First, let me try to give you an idea about what snapshots. Snappy will maintain snapshot for a very short period of incoming traffic. We then can combine multiple snapshots to estimate the entire queue's content. In this illustration, say that we have a snapshot of size 3. So when the packet comes in, we'll add it to the most recent snapshot, which is S1. And when the packet comes in, we'll add it to a snapshot as S1 again. When this packet goes out, we do nothing. So we only add packet to snapshot when they come into the queue. So say that the red packet comes in and snapshot 1 is full. Now we should move on to snapshot S2. When a burst of packet come in, we'll quickly fill out a few snapshots. At this point, the queue is really, really long. And we can see there's a threshold we set, and now the queue is longer than the threshold we set before. So say that the purple packet comes in and goes into the queue. We realize it's very, very long. So we are very curious, who are causing the queue buildup right now, or who's in the queue right now? However, we cannot really answer this question precisely because we didn't track who's going out. However, we can approximate the answer by looking at a few recent snapshots. In this case, by looking at snapshot S2 and S3, we can check with this part of the packets. So now we can give an approximate count of who's inside the entire queue. In this case, apparently the red flow is small and the green flow is large. So green flow is probably causing the queue buildup. So now say that another green flow comes in and it will get added to the queue. And then you can query the data structure and realize, oh, I am causing trouble. I am one of the packets coming for the large flow. Here we made two observations. First, when the queue is long, we have lower relative error. We can count from more than one snapshot and lowering the error we made when we approximate based on slicing them into snapshots. The second observation is we care about only heavy flow, not everyone. So for a snapshot, we could use clever data structures to try to accurately count it. We made a third snapshot that there's only limited number of snapshots needed because the queue have a limited size. So say that most of them are full, but one of them are being written. We can try to clean one of the snapshots and do a round robin so we can use it later. So say that packet are coming in, and we can also clean the oldest snapshots we have. And once the snapshot is filled, we have one more snapshot that's empty. Now, we can simply rotate the rows of all these snapshots and have one more empty snapshot to write. This system implementing a programmable switch, but how accurate it is. In evaluation, we show that we can cut as much as 90% of the heavy flows in the queue whenever there's a microburst, and we cross less than 10% of false positives, only using less than 2 kilo, And how many snapshots needed? We only need 4 to 8 snapshots. And we built a 4 snapshot prototype to up and running in our testbed, and we're also trying to deploy that in a production network. And we only need to use less than 2 kilobytes of memory in the programmable switch, which is less than 1% in most of the model we have today. And more importantly, these 2 kilobytes of memory serve all the data structure, being round robin access, etc., create a possibility for us to use the other memory to simultaneously analyze these heavy flows and eventually lead to a better action to add on these flows. I want to show this figure to show the relationship between precision versus snapshot memory usage. The precision here is how accurate we try to find the heavy flows. In this way, we know that the true memory need of our algorithm. The x-axis here is about the number of counters we have in the sketch data structure for every snapshot. One counter should be about 4 bytes. And then the y-axis here was the precision by catching the heavy flows. As we can see, the trend here is giving more and more memory, you get higher and higher accuracy. However, you need no more than 32 to 48 counters. Here, the line is a realistic upper bound we want to look at. So look at this line, we can see that you need about 40 counters or about 160 bytes, not kilobytes, just bytes, to achieve 90% accuracy. And now we'll want to also show the result of how many snapshots we need to get a high recall. So the number of snapshots means that if you have more number of snapshots, it means that at the end, both end of the queue, when we try to query entire snapshots, you get a lower rounding error. If you only have 4 snapshots, for example, you can only query like 25%, 50%, or 75% of the entire queue, which causes some rounding error when you try to find the heavy flows. In this figure, we can see that just giving 4 snapshots should be more than enough for most of the applications. It gives us higher than 90% of accurate recall accuracy. We also have an ongoing extension of our project to try to collaborate with AT&T and deploy Snappy on real network and catch microburst copies in the wild. As we shown earlier, there are microburst traffic in the production network, and we really want to know which flows or which applications is causing some microbursts and try to optimize for these applications. In carrier networks, we cannot replace all devices overnight by programmable switch, and it's also very risky to try to just directly deploy a new hardware on existing networks. However, we still have a demand to know details about traffic, especially microbursts, inside these networks. We have a novel solution here. We can try to use the tapping links already available in our network to try to feed the traffic into a programmable switch. Here, the packets going in and out of the legacy switch will be monitored by a programmable switch. We will first try to match both copies of the packet and get a queuing delay. Then we can still use the same Snappy snapshots to try to analyze which flows is causing microbursts in the traditional switch. We can do this even if the legacy switch does not support any kind of queuing measurement, because the programmable switch always see both copies of the packet and can estimate the queuing inside the legacy switch. We can also think about ourselves that what other application can benefit from this tapping setup, especially this two-sided tapping instead of one side. Given one link tapping, we can only do things like analyze the link level traffic. However, given both tappings, we can analyze the congestion and queuing dynamics inside the switch. Now let me give a summary of today's talk and give a brief overview of the work in our lab. So programmable switch gives us better opportunity for better measurement. It does not give us some new data, but we can perform some analysis on every single packet, which is by itself can give us new data. However, we are constrained by partition memory and simple arithmetic. This creates some challenge for algorithm designer to design a good algorithm, to do right data reduction and save the data inside data plane, and also to let it run, able to run on programmable switches. Data reduction is key here, that we want to find the right answer to saving the memory. And for most of the case, for most of the traffic, we didn't save anything in memory. Today, the first project we discussed today, PRECISON, try to find a heavy flow on the link. It used recirculation with a very small probability to try to make sure that for most of the case, packages flow through the pipeline. And for very small probability, we can do something complicated. However, it will not impact regular traffic or regular traffic throughput. The second project, Snappy, try to find heavy flows in the queue. We use snapshot and aggregate snapshot and rotate them to try to always maintain a timely view of which packets are in the queue, even if we are not trying to analyze who's getting out of the queue. This way, Snappy enables us to measure short time interval queuing dynamics that have never been done before, and allow us to act on this packet immediately if we detected there's a microburst. With the right data reduction, we can focus on the interesting O1 small number of data while not monitoring the ON level of the long traffic. Again, here there's a trade-off between, there's a difference between precise measurement and approximate measurement. The precise measurement is very hard to run at line rate because you need to look at every single packet and you have to deal with 100 Gbps or more of line rate traffic. Here we use approximate measurement that can save memory by using sketches. It's using very simple logic, which is hardware friendly. And we do have an accuracy issue here, but usually we have an accuracy memory trade-off. If you have more memory or more stages or more resource, we can have much higher accuracy. And usually the accuracy needed for application, we can achieve it just using adequate amount of resource available in today's hardware. As a future work, we're trying to extend precision to hierarchical heavy hitter question. For example, which IP block is DDoS in my network? For Snappy, we're trying to also support hierarchical keys and the non-FIFO queue settings. And we also have an ongoing project about how to combine multiple approximate queries together in the data plane. In today's talk, we essentially presented a few measurement building blocks. And in our lab, our research focused on many different measurement queries with many different building blocks. Most of them are stemming from the hardware constraint. On the left column, we have a lot of the hardware programming constraints posed by these programmable network switches. However, these constraints are not roadblocks to us because we always have corresponding solutions. For example, in today's talk, we presented some solutions highlighting green, highlighting orange to solve the limited memory size issue, to solve the memory access, partition memory access issue, and as well as cannot visit too many memory locations. There are more to come. I'm definitely sure there are more constraints and more challenges to come, but there are definitely also more solutions to come. The takeaway is we shouldn't limit our imagination by the data plane's constraints. Even if we have the programmable switch, today's programmable switch have these constraints, we can always have some solutions to still successfully get our measurement task. So our question to ourselves should be, what's the right measurement to have? And given this new model, what can we achieve that previously cannot be achieved or cannot be measured? I would like to thank all my collaborators. Without them, I cannot get all this project done. And also, I would like to show I use some of the image from the internet, or these are the image credits. And now I finished my talk. I will be happy to take any questions. So for discussion, I want to spark 3 questions to the readers I presented earlier. So first of all, when is approximate measurement acceptable? Or for which use cases it's actually not acceptable to approximate? The second question is, besides microbursts, what other measurements were impossible before and now are enabled by data plane programming? And the third question is, given these real-time measurements, what are the appropriate actions on these packets? So for example, dropping a packet may not be the most appropriate action, even if you're having congestion. So thank you, everyone, and I will be happy to take any questions and we can have discussions.
So Danny, this is Jack. I do have a question, and thanks, by the way, for giving the talk.
Hi, Jack.
For Snappy, I mean, it's excellent. You have a very nice algorithm that identifies the heavy flow using this computational model. But let me ask this question. As long as, I mean, given that you can identify when the queue length exceeds some threshold, how much worse would it be if you simply randomly dropped packets when the threshold has been exceeded? In other words, if you're randomly dropping packets, you're still likely to drop a packet associated with the heavy flow. How much worse would that approach do? Do we have any sense of that?
Okay, great question. So in fact, that's what most switches are configured. The default configuration is random early drop. So whenever the queue goes longer, they switch to randomly drop packets. So yeah, most of the time, the heavy flow get penalized most heavily. But there's some random chance that small flow also get penalized by being dropped. So for example, I'm just a small TCP flow. I'm just sending some very small file. Supposedly it should finish fast. However, one of the packets get randomly dropped. And the TCP connection will immediately try to cut back because it just see a drop and it will try to slow down itself. So in these cases, if there's a heavy flow like crushing the network and queue is long, will just randomly get some impact. If we can precisely find out which one is heavy, then we can only constrain action to the heavy flow itself. So the small flows going through the network will never experience this issue. So does that answer your question a little bit?
It does, thank you.
Yeah, so we do have some experiment in our lab to try to send mixed workloads, including heavy and small flows, and measure the flow completion time. And we can show that after enabling Snappy, we can lower the median completion time slightly because the small flow now get finished faster. However, the large flow definitely finish slower now because they will get penalized.
So this is Nate. Thanks for a really nice talk. I wanted to actually just throw your first question back to you. You've been working with AT&T, I know, and also at least getting going with a deployment of the campus network, I believe. What are the cases where approximation seems to be acceptable, or what are the bounds on the approximation you need to get useful information from these kinds of techniques for specific, for specific queries?
So yeah, so we can start with something that's unacceptable. For example, billing. You probably would not want to bill your customer based on an approximate payment. So yeah, there are definitely some cases in the business sense that we do not want to approximate. So for example, if you have an SLA agreement with the customer to say 99% of the chance I should blah, 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 then you definitely want an exact measurement to your customer to show that you actually do this 99% of the time. You don't want to say that approximately 98 plus 2% of the time I'm accurate. However, well, in this case, approximation still helps the internal, like it's helped internally, like budgeting, for example, or you can just detect SLA violations before it actually happens. Approximation measurement can help, but when it depends on like different external parties try to have an agreement, then you don't want to use approximation at all. And I think most of the use case here is for performance monitoring and performance, how do we say that? Performance optimization. So if you want to say that you find a heavy flow, you penalize that randomly, and you can have some error room, and the action was not very aggressive, then even if you made a mistake, that's fine. Then overall, the system will get a much higher performance out of it. And sometimes when people do performance diagnostics, you might be able to use approximation. Because, for example, I want to debug the network. I want to try to find a heavy flow. And if it is the issue, I can see whether it actually caused the issue. In this case, if I just get a random list of 10 flows, and I know 6 of them is actually causing my trouble, 4 of them is not, maybe the tool is still very valuable to the user. I think the strength here is we have real-time monitoring in real time, and it will be really useful for the system itself to correct the issue or immediately give some report to human. So we get some very timely result. Is that measurement usually takes some time to actually get out. So in this case, if the only thing you have is this approximate measurement, you definitely want to use it. Actually, this also relates to one of my other questions. So what can you do, or what should you do in data plane? This builds on that you have something to do in data plane, but also you need something to be able to look at in data plane. If outside of data plane, you go up to control plane, you collect some traffic, you analyze it later, and someone told you, this is the traffic that's causing the microburst. Well, it's very useful for humans. We can call someone and they can fix their code. But it's not useful for the switch itself. It needs to know immediately whether to let a packet go through or whether to drop it or whether to do something on it. In this case, we just cannot accept that you get an accurate measurement, but it's 1 millisecond late. You just immediately get an approximate measurement.
So I have one other question that's a little bit of a broader question. Both of these systems use quite a bit of creativity and ingenuity at the algorithmic level, as well as at the architectural level. You have a very good knowledge of how PISA works in order to get the results. Do you have any sense of maybe a set of general techniques or some more systematic way to go from a monitoring objective down to an implementation that's this sophisticated? And it may be that it's still early days and we're basically taking insights from the streaming and space efficient data structure theory community and sort of applying them in practical networking domains. But it would be obviously very cool, and I think related to your last 2 points on discussion, if there was a way to do this systematically that didn't require PhD level insights, or especially if you're composing queries, making trade-offs about resources and accuracy in principled ways. Do you have the vision of having this very fine-grained measurements that are done efficiently on programmable hardware is really compelling? I'm just curious where you think the area will go in terms of these query or runtime systems.
So I have to say that I don't have a perfect answer for this because we're in the early days. But my observation right now is if someone can define a good measurement like query language or some agreed upon semantics to say what is the query or how to do the query, then definitely we'll have a good division of labor between the people who write a query, which are the operators, and the people who have better knowledge about the hardware and how to write, the data structure community, streaming community, etc. We can have an agreed upon interface. And once we have that, then people closer to the hardware side would have very good optimizations and compilers and everything to try to execute the query in the data plane. However, the people who are the people who are outside the community just need to use the agreed upon language. So for example, SQL is a very good language, and people just use it in database community. And whenever someone can write SQL, they just write one line and get out of it. And then everyone else in the database, everyone in the database community try to crazily optimize their engines on hardwares, etc., to just execute that query language that was agreed upon. Some of our research in our research group, for example, Sonata, was trying to propose one of these query language, but they're often still too restrictive in some way. I think we'll soon have a more like general query language to define what to ask, what was the query someone want to ask. And once we have that, we will definitely have some compiler to automatically try to adapt this query into data plane. Or at least give some result of, give an best approximate of what you want to ask. Maybe it's not a very good approximation, but we'll guarantee that we'll always get something out of it.
Great, thanks.
Okay. I think I still have a lot of questions for everyone about what's the best appropriate actions. So let me see. So let me try to discuss a little bit and try to spark some ideas. So what can you do when you see a network flow is really heavy in your system? And what can you do now? If you drop the packet, it could be too aggressive. For example, even say the buffer was not full yet. If you drop the packet and the flow get heavily throttled back, and the customer will knock on your door and be angry to say, I buy from my premium, traffic, whatever, and why my packet dropped very soon. And you can also easier mark the flow, but it doesn't really work if you're in a wide area network because you have a high latency. By the time the sender knows that it's aggressive, it's already too late. It could work on data centers, but not really sure if it's in wide area. And maybe you can reroute the traffic, but maybe it's not possible. In data centers, you have multiple routes to go, but in wide area network, you only have one route to go to that place. So you cannot really reroute or load balance the flow in some way. Maybe you could charge higher cost to customer to say, it's okay you send whatever we want, but if you cause some burst, I will charge you more because you cause everyone else to suffer. But again, this is not immediate action. So giving the data plane ability to do immediate action, what's the right thing to do? It remains an open question. So one of our current thought was maybe we can just use separate queues for bursty flow and non-bursty flow. So it's similar to what you have in priority case. Like if you are high priority traffic, like 911 call, then it always goes through, you always have priority over other flows. But what we think of was everyone was always having high priority and short latency. But once someone is bursty, it causing trouble for everyone, not just himself or herself. Then the flow will move to a separate longer queue that you can just queue there and queue by yourself. And everyone else still have a very short latency. But maybe this is not the best way. But
so when you're referring to rerouting, are you referring to like a traffic engineering timescale activity of rerouting the entire flow?
No,
or are you just referring to misdirecting individual packets in a burst?
I think it's more like, when you say traffic engineering perspective, I don't know what you were referring to, but maybe, let me say it this way. So it's like for the next 1 millisecond, you probably want to do something. But this effect should be immediately like undo once the microburst is gone, which is usually happening in millisecond timescale. So it should, in the traffic engineering sense, at the beginning, we should say, we want this flow to go through this route. However, there are a few other possible routes that allow this flow to go if it's getting congested or getting bursty, and this flow was the heavy flow. So in this case, it's like if you are causing a microburst, then immediately starting now and ending next microsecond, ending next millisecond, this flow will split traffic or divert traffic to another link. So this link will not have congestion. And maybe next link is very idle, so it's always fine. So is it clear?
I can't help to note that we're kind of doing everything very myopically here. We're looking at a queue and a switch, not in any end-to-end sense. So somehow charging higher cost to a customer when in fact the customer could have little to do with the actual creation of the microburst. It could, for example, some bugs upstream or something.
I agree.
Seems like a very difficult approach.
Yeah, so this is just a crazy idea listed here. So what can we do? Like, by the way, these two ideas, like charge higher cost or ask developer to change the burst behavior, are all long time scale. Like, it doesn't happen in a millisecond. So what can we do in the switch itself, or what can we do when we actually is having congestion next millisecond? If you don't do something, you will have a congestion, you have packet drops, but now we can do something, then what can we do now? Definitely not start to make a phone call to the app developer because they will not pick up in 1 millisecond. Just a joke, yeah, but maybe that's the eventual way. Like if this happens over and over again and people start to investigate and see this is happening in this app or this kind of payload, then we definitely need to figure out why. There's an anecdote that in Microsoft, they observed this kind of microburst and they realized it's one of the developers, they don't know too much about network. They use TCP a lot. They want to have lower latency. So they artificially make the TCP sending window very, very large to make sure that when they send traffic, they will not be throttled by congestion control. So basically you made a phone call, we have some discussion, and then they will make their app behave better by maybe not using TCP at all and still get their lower latency and does not cause trouble for everyone else.
All right, we should probably wrap up because it's past 4 o'clock, by 5 minutes left. Thank you again for a great talk. If people want to stay on the call and keep talking, that's fine. But,
yeah, thanks everyone for your participation, and I really appreciate the question and discussion. So I will be hanging on for a while. If anyone have more questions, we can have more discussions. Okay.